All right, this video is on Chapter 2, Section 4. The topic is real zeros of polynomial functions. What we'll learn about long division and the division algorithm, remainder and factor theorems, synthetic division, rational zeros theorem, and upper and lower bounds. And while you're learning this, these topics help identify and locate the real zeros of polynomial functions. So here's the division algorithm for polynomials. Let f of x and d of x be polynomials with the degree of f greater than or equal to the degree of d and d of x not equal to 0. Then there are unique polynomials q of x and r of x called the quotient and remainder such that f of x equals d of x times q of x plus r of x, where either r of x equals 0 or the degree of r is less than the degree of d. So basically what that's saying here is that this function f of x equals the divisor times the quotient plus any remainder that there is. The remainder could be 0. If it's not, then the remainder, its degree, must be less than the degree of the divisor. So the function f of x in the division algorithm is the dividend, and d of x is the divisor. If r of x equals 0, we say d of x divides evenly into f of x. So here's an example using polynomial long division. We want to use long division to find the quotient and the remainder. And if you want to pause the video and try this in your notes, go ahead and do so. But we want to take 2x to the fourth plus x cubed minus 3 and divide it by x squared plus x plus 1. And the key is when we're using polynomial long division is we have to use zero coefficients for missing terms. Okay, so that's the one thing that we have to remember. So we have to use placeholders. So here's how this problem would look in a long division format. We have our dividend, 2x to the fourth plus x cubed plus 0x squared plus 0x minus 3. We have our divisor, x squared plus x plus 1. And the process is x squared goes into 2x to the fourth 2x squared times. So we put 2x squared on top of our fraction bar, and we use 3 terms. We put it above the third term because there are 3 terms in our divisor. So we go ahead and we take 2x squared and we multiply it by x squared plus x plus 1. That gives us 2x to the fourth plus 2x cubed plus 2x squared. We go ahead and subtract those from each other, vertical subtraction. Okay, and that leaves us negative x cubed minus 2x squared plus 0x. Bring this down. We need our 3 terms here. And then we go ahead and ask ourselves, how many times does x squared go into negative x cubed? Well, the answer is negative x. So we put minus x up here. Negative x times all of these terms gives us these 3 terms. Go ahead and do our subtraction again, and we're left with negative x squared plus x. Bring down the minus 3. Okay, and one more time, x squared goes into negative x squared negative 1 times, so we put a minus 1 up here. Minus 1 times x squared plus x plus 1 gives us these 3 terms. We go ahead and do our vertical subtraction, and we're left with 2x minus 2. So the answer is this part up here. It's our quotient, 2x squared minus x minus 1. And then we take our remainder down here, 2x minus 2. We put it over our divisor, and that gives us an extra term in our quotient. So we have this thing called the remainder theorem. If polynomial f of x is divided by x minus k, then the remainder is r equals f at k, meaning the value of the original polynomial evaluated at k is the remainder. So here's how this plays out. Find the remainder when f of x equals 2x squared minus x plus 12 is divided by x plus 3. So the remainder theorem says we just take our value of our function at -3, okay, because if we're dividing f by x plus 3, that gives us a 0 of -3, potential 0 of -3, okay, and we evaluate the function at -3. And so the value of the function f at -3 is 33. So that tells us that when we divide f by x plus 3, we get a remainder of 33, which tells us that -3 is not a 0 because there's a remainder. So this is a way that we can very quickly tell if zeros that we think might possibly be zeros are in fact zeros. We have another theorem called the factor theorem. A polynomial function f of x has a factor x minus k if and only if f of k equals 0. And this is what I just mentioned. If we evaluate the function f at some value k that we suspect to be a 0, and the value of that function is in fact 0, meaning no remainder, then it is a 0 at k. So here are some fundamental connections for polynomial functions. For a polynomial function f and a real number k, the following statements are equivalent. Number 1, x equals k is a solution or root of the equation f of x equals 0. Number 2, k is a 0 of the function f. Number 3, k is an x-intercept of the graph of y equals f of x. And 4, x minus k is a factor of f of x. Again, those are all equivalent statements. And now we're going to take a look at synthetic division. We want to divide 3x to the third minus 2x squared plus x minus 5 by the linear factor x minus 1 using synthetic division. So let's take a look at what this looks like. So in a synthetic division problem, okay, remember, this is our potential 0. Okay, potential 0. The 3, the -2, the 1, and the -5 are the coefficients of our terms in our polynomial. Okay, so we bring those down. All right, those coefficients, bring those down. And so this would be the setup when we start. Our first coefficient, we bring it down below the line. Okay, so we bring the 3 down. And then we go ahead and multiply 1 times 3, which is 3, and we write that under our next coefficient. And that's what you see over here filled in. Okay, every vertical column here, we just combine those two numbers. So we get a 1. 1 times 1 is 1. Bring 1 over here. 1 plus 1 is 2. 1 times 2 is 2. Bring a 2 here. -5 and 2 combine to be -3. And this is the completed form of that. So this number right here at the end, when we finish, if that's not a 0, then that value is our remainder. Okay? And we take that value, that value is actually the numerator of the remainder. So what we do is we take these first 3 coefficients, and those first 3 numbers are the coefficients of our quotient. So 3x squared plus x plus 2. And then we take our last number here, -3, and we put it over our divisor to give us our remainder term. That's where the -3 over quantity x minus 1 comes from. And that's called synthetic division. We use synthetic division a lot when we're looking for roots of polynomial functions, verifying whether things are roots or not, and we have some other things that we can use synthetic division for as well. So we have this thing called the rational zeros theorem. Here's what the rational zeros theorem says. Suppose f is a polynomial function of degree n greater than or equal to 1 of the form f of x equals a sub n x to the n plus a sub n minus 1 times x to the n minus 1, and so on until we get to a sub 0, our last term, with every coefficient an integer and a sub 0 not equaling 0. If x equals p over q is a rational zero of f, where p and q have no common integer factors other than 1, then either p is an integer factor of the constant coefficient a sub 0, And q is an integer factor of the leading coefficient a sub n. We got a little typo here on our slide. These g's, these should be bullets. So this is a bullet, and this is a bullet. So this rational zeros theorem says p are the factors of a sub 0, so the last term in our polynomial written in standard form, and q is an integer factor of the leading coefficient of our polynomial in standard form. And we also have this thing called the upper and lower bound test for real zeros. Let f be a polynomial function of degree n greater than or equal to 1 with a positive leading coefficient. Suppose f of x is divided by x minus k using synthetic division. Here we have typo again. These g's are supposed to be bullets. If k is greater than or equal to 0 and every number in the last line is non-negative, meaning positive or 0, then k is an upper bound for the real zeros of f. So after we use synthetic division, when we scan the last line, meaning below the line in the synthetic division, after we've combined all our numbers, if everything is non-negative, then k is what we call an upper bound for the real zeros of f, meaning there are not going to be any real zeros greater than that value of k. If k is less than or equal to 0, and the numbers in the last line are alternately non-negative and non-positive, then k is a lower bound for the real zeros of f. So if this is the case after synthetic division, then we know that k is the limit, or the lower bound, like it says, of the real zeros. There aren't going to be any real zeros that are less than that k value. So we can kind of narrow down an interval. Once we determine two zeros of a function, we can kind of narrow down the interval where we look for the rest of our zeros if we know that we have an upper bound and a lower bound. Everything else is going to be between those two values. So find all the real zeros of f of x equals 2x to the 5th minus x to the 4th minus 2x cubed minus 14x squared minus 6x plus 36, fifth degree polynomial. Find all the real zeros and identify them as rational or irrational. So the potential rational zeros from the rational zeros theorem, we take all the factors of our last term, 36, okay, and put them over the factors of 2. So all the possibilities, we've got to take every single factor of 36 and put it over every single factor of 2 and list out all the possibilities here, okay? So all of these are all possible zeros of our function. Okay, and sometimes this seems like a bit of a daunting task to then narrow this down to a few select values that are zeros, but we have a few tools that we can use to help narrow down our search. One of them is our technology. So if we were to graph the function and take a look at that function, the graph suggests that only x equals negative 3 halves, x equals 3 halves, and x equals 2 can be considered, just because of the nature of the graph, okay? In this graph here, we have these tick marks because of the window here that we're given. The x scale is negative 6 to 6. So each one of these tick marks on here is a value of 2. So this is 2, this is 4, this is 6. Negative 2, negative 4, negative 6. So that's how this assumption right here is made. Now synthetic division shows that only x equals negative 3 halves and x equals 2 are in fact zeros of f. Okay, so I'm not going to show that work, but we could work that out and verify that. So what we know about f is that f of x equals the factor 2x plus 3 times another factor x minus 2. And then after those two synthetic division steps, the coefficients that we would be left with would be a cubic function x cubed plus 2x minus 6. So this factor right here can generate some more zeros. So if we take a look and let g of x equal that remaining factor x cubed plus 2x minus 6, and we go ahead and graph it, well, the potential zeros from the rational zeros theorem are positive negative 1, positive negative 2, positive negative 3, positive negative 6. But the graph shows that these values are not zeros. Again, our scale is negative 6 to 6, so each one of these tick marks is 2. So the graph shows that these values are not zeros of g, because clearly there's a 0 here that's less than 2, and it's going to be some decimal. value. So f has no more rational zeros. So if we use our graphing calculator with either function, we can use the zero tool to go ahead and find that last zero. And it's approximately 1.456. And the upper and lower bound test can be applied to f or g to show that there are no zeros outside the viewing window shown. And the values that we would test would be here and here. And those were these values down here. -3/2 and 2. -3/2 is the lower bound and 2 is the upper bound on our zeros. And we have an irrational zero in between those two of approximately 1.456. So another example here, we want to find all the real zeros of f of x equals 2x to the 4th minus 7x cubed minus 8x squared plus 14x plus 8. So if you want to pause the video now and try that, I will go to the next slide and show you the solution. So our potential rational zeros using the rational zero theorem are all of these here. Compare the x-intercepts of the graph and the list of possibilities. So what we're going to do again is we're going to list our possibilities, we're going to use our technology to generate the graph, and then we're going to compare these two to see which in fact are potential rational zeros. So based on the graph and the list, we have two, 4 and -1/2. So we're going to use synthetic division, and we'll choose 4 first. So we will use synthetic division to see if 4 is a factor of our polynomial. And lo and behold, here at the end we get a 0. So that tells us that x minus 4 is a factor of our polynomial because 4 is a 0. So remember, the factor and the 0 are going to have opposite signs. Now, if we take -1/2 and go ahead and divide that into our cubic that was left, okay, that's what this would look like here. And again, we get another 0. See, every time we do this synthetic division step, we're breaking down our polynomial into 1 degree less, 1 degree less, until we get to the point where we have a quadratic, and then we have many tools that we can use to solve a quadratic. So -1/2 is also a 0, so this tells us that our original function f can be broken down into, now where does the 2 come from? Well, 2, 0, and -4 are telling us that 2x squared minus 4 is left as a factor, but we can factor out a 2, x squared minus 2. So the 2 goes out front, and the x squared goes here at the end. And then we can use, like I said, we can use some of our multiple methods to solve this quadratic. The simplest way is to just go ahead and use square root methods since we don't have a middle term here. So go ahead and isolate x squared on one side, take the square root of both sides, x equals plus or minus the square root of 2, and that's where these come from. Okay, so some review questions that you should be able to do after this lesson. Go ahead and try these, pause the video, work these out, and when you're ready to go on to the solutions, go ahead and play the video. And if you have any questions about any of these problems or anything in the lesson, please be prepared to ask that in class.